I'm gonna get started in about 2 seconds. You're the only one here so far.
Okay.
So, but I'll be posting it tonight anyway. So if anybody shows up, by the way, I just want to remind everybody uh, since this is going to be recorded and everything, I want to remind everybody that I'd show up on Thursdays at 5 o'clock in case anybody has questions. Even though the class doesn't start till 5:30, I might have to send out a email and ask anybody if that's even helpful. Because when nobody shows up, I'm just wasting my time. So I might end up not doing it if it's not helpful to anyone. But anyways, currently it's still going at 5 o'clock on Thursdays. I show up just in case anybody needs some extra time. Also, of course, I always stay afterwards if anybody has any questions. So I'll be doing that. That'll be continuing. So, all right, it's 5:30 now, so I should go ahead and get started. You can chat me your first and last name. That way I'll have you down for roll, even though, like I said, roll doesn't count too much since this is an optional attendance issue. But we are starting chapter 22 today, and I've discovered that chapter 22 is going to take me a little bit longer than I thought. So I'm going to have to push the homeworks back, and I've already done that. I've pushed the homework grades, the homework due dates for chapter 22 back a little bit, so y'all have more time. But most of it I can get done today, or at least get you started. So we're going to go ahead and get started. I'm going to start by sharing my iPad screen. I've written up some notes already, so I wouldn't have to write them while you watch. And you can, of course, download them. Remember, I put these notes up on my YouTube channel, or excuse me, on my Google Docs page, which I'll have a link to in my helpful documents and links module. But the notes are always posted in my 242 uh, Google Docs drive, are actually a folder within my Google Docs drive. And I also have the ones for 241 and the similar one, but you have access to both of those by being in my class. So chapter 22 is Gauss's law, but in order for us to make sense of Gauss's law, we had to teach you something about something called electric flux. It turns out there's a quantity called flux that's really important. It turns out it's not only important in electrical, when we're dealing with electric fields and electricity, but it's also important when we deal with magnetic fields. So there's actually going to be an electric flux and a magnetic flux, and we'll have both of them using the same symbol, capital Phi, as you can see down about almost halfway down the screen on this page. You see that phi on the left hand side of the equals. Uh, the difference would be is normally we just call that phi, and when we do with the magnetic field, we'll say phi, and then we'll have a subscript b for the magnetic field. We use the symbol b for magnetic field, and of course the formula that you see there is E times A times cosine theta. In the case of the magnetic one, at least in this special case, it would be B as in magnetic field, B as in boy, times A times cosine theta. But let me go ahead and explain what it is. Electric flux phi is a measure of the number of electric field lines that penetrate a surface perpendicularly. So I had to put the number in quotation marks because it's not exactly true that you're quote unquote counting. It's more like you're multiplying the magnitude of the perpendicular component times the magnitude of the area. Uh, and from that getting an actual quantity out that comes out in units of Newton meter squared per coulomb. So that's really what it is, and that's why I put the word number in quotation marks. Calculating the flux is easy when the surface is flat and the electric, left off a crossing of a T on the word electric there. Uh, the is Calculating flux is easy when the surface is flat and the electric field is uniform. In that case, it is just the perpendicular component of the electric field multiplied by the area of the surface. So I drew a little drawing there to the right, and that drawing is supposed to be a flat surface. It sort of looks like a window frame, and that would be a fine surface as the actual window itself. But we're imagining the flat part is a literal flat pane that extends from the bottom up to W and from the right, excuse me, from the left up to L. And therefore, the area of that surface is L times W. That's why I've written the A vector with magnitude around it. So I've got those absolute value bars that shows the magnitude of the A vector is L times W. So what we're doing to actually calculate this flux is we're first creating a vector that's perpendicular to the surface, as you can see with my little blue lines right here and here. Those are supposed to show you that it's actually perpendicular to the actual surface. And that's the area vector right there. And its magnitude is supposed to be equal to L times W, as you see right here. So once you define that, you probably would see that there's some arbitrariness in the A that I drew, and that's why I drew negative A over there. Negative A would be an acceptable version as well, at least right now, and I'll explain that in the next paragraph. But the main thing is we want to take the component of the electric field that is actually perpendicular to the surface. So what we do is we imagine this electric field, which is that vector right there. We imagine breaking it up into a component that's parallel to the area. So that's E parallel to A, and that's this one right here. Okay, but then it has a perpendicular component, and we don't need that one at all. You should be able to see that the parallel component, E parallel to A, is actually uh, equal to E times cosine theta. And that's why I drew all that on there with the theta. So that taking E and multiplying it by the cosine of theta, where theta is the angle between the A vector and the E vector, automatically takes the component of E that's perpendicular to the surface because we defined A to be perpendicular to surface. So the drawing is helpful, but since the surface does not have a clear inner volume and outer volume, i.e., it is not a closed surface like a spherical surface or the surface of a soup can, the direction of A can be as shown, or it could be given by the vector negative A. In other words, there's an arbitrariness. There's a infinity of arbitrariness if you just want A to point in any direction whatsoever. In fact, if you don't go with perpendicular, then you've got an infinity of directions parallel to it that would work. So you can at least reduce the number of choices down to two if you just say perpendicular. And when you get it down to perpendicular, you say, okay, well, I've got two choices pointing this way as we see the blue one is, or pointing the other way as we see the black one is. But if you have a closed surface, one that has a definite inside and a definite outside, then we define the A vector to point away from the inner volume. So we define the area vector to be perpendicular to the surface and pointing away from the inner volume of a closed surface. So if it's not a closed surface, we don't have anything to say. It's just going to be either A or negative A as drawn in that diagram. But if it is a closed surface, then the A is uniquely defined to be pointing from or away from the inner surface or the inner volume of the closed surface. When the surface is closed and therefore not flat either, we have to divide it up into many small surfaces that are so small they are flat, and the E field is uniform over the small area dA. So we're going to dice up, for instance, a sphere into smaller and smaller areas, and we'll keep doing that until we get a way where we can find that the electric field is uniform over the whole surface dA. Once we've gotten dA that small, then we've gotten small enough. And then we just take E times A vector magnitude times cosine of the angle between them. And we do that for each of those little surfaces. But the surfaces are so small, we have to do an infinite sum. Therefore, the sum turns out to be an integral. So then we have to add up all the fluxes due to each small area dA by integrating, and that's the actual formula that we have for the electric flux in general. Now, that doesn't say it's over a closed surface, but that is the rule. The flux is always the integral of E dot dA if you're talking about electric flux. If you're talking about magnetic flux, which we will later, it's phi sub B or phi sub B, B as in boy, is equal to the integral of b as in boy vector dotted with dA vector. So we're going to show you how to do some of this integrals with derivatives or excuse me, with dot products and stuff like that. We're going to show you that as well. So first off, let's start with a really simple example of a small flat surface. So what I've drawn here is a small flat surface. It's supposed to be 20 centimeters tall by 10 centimeters wide. I've got it drawn in 3D so we can see a little bit of it. And the blue vector is drawn such that it's supposed to be perpendicular to that surface. The E vector is the red one, and we see that it makes an angle theta with the vector A. So I'm asking if E is equal to 300 newtons per coulomb, and I'm saying 300 is to 3 sig figs. That's why I've got the fourth sig fig with an underscore, and it's 300 newtons per coulomb. And theta is 30.0 degrees. What is the electric flux? In this case, the electric flux will be, I'll show you now. Oops, I gotta get my pen back instead of my little laser pointer. So solution, I don't know where that cross between a cursive S and a regular S came from, but I kind of like it, so that's cool. What we're using is flux is equal to E times A times cosine theta, which you could also represent as E dot A, and that's sort of the whole point. But either way, we're going to go ahead and do that. We know our values. E is supposed to be 300.0 newtons per coulomb. That's the units of the electric field. We'll find out later the electric field also has units of volts per meter, and that's a much better unit for most things. And then the area of this, which we really need to put in square meters, not in square centimeters. So I'm going to write this as 0.100 meters for the width, and then 0.200 meters for the height. And then I'm going to take it and multiply it by the cosine of 30.0 degrees, which, if I remember correctly, is root 3 over 2 or 0.866, something along those lines. So we're going to take 300 times zero point 0.1 times zero point 0.2 times cosine 30, and that gives me 3 root 3, which is super helpful. These graphing calculators, they always by default try to reduce the square roots to the nicest, most concise number, but that's not a decimal, so it's always a pain in the butt. So this one turns out to be 5.19, and the next digit is a 6, and that is newtons meters squared per coulomb. So that's actually the electric flux through that surface. Anybody have any questions for that on that one? All right, so that's the key to understanding it. Now, what I want to do is I'm going to tell you that a couple things have to be recognized. One, we've got to sort of solidify our idea of electric field lines. Your book did that in chapter 21. It talked about how you can sort of make the electric field line drawings for point charges and stuff like that. You can make them quantitative. For instance, let me show you how. If, for instance, I drew a positive point charge, oop, I guess they decided to make that one into a square instead of a circle. If I decided to make a positive point charge, darn it, why did it erase that? What a jerk. Oh, it's still erased it. There it is. Okay. So now I'm going to make a little positive sign in it. Now, this is a charge that I'm going to assume is Q. Okay. Now, what I'm going to do is I'm going to go a distance of one whole cube away, and I'm going to draw a field line. And then I'm going to go to the right one whole cube away, and I'm going to draw another field line. And both of these field lines are drawn in a way that I'm trying to make them exactly the same distance from the center of the charge, as well as make them the same length. Because it turns out, if you look at the equation for the electric field of a point charge, the electric field of a point charge only depends on the magnitude of the charge directly and inversely to the square of the distance between the charge and the point in space. Well, if the point in space is a fixed distance away, then the R is going to be always a constant, so we get a constant magnetic or electric field magnitude. So that's what I'm trying to do here. So here's my third vector, and there's my fourth vector. So that's just the charge positive Q that and the field lines that represent it. Now what I'm going to do is show you a charge of 2Q, and for that case there's a couple different ways we can do it, but actually I wanted that to be a perfect circle, so let me redraw that real quick. So I'm going to draw a near perfect circle. Okay, close like that. And this one also is going to have a positive charge. And this time the charge is 2Q. So the way we represent that is we again draw a set of arrows a fixed distance away and with a fixed magnitude. But because this is an actual, actually, I got to get a little further away from that one and fix it a little better. Since this is actually supposed to be a scale representation, if you will, then I need to be very careful and make it representative of the fact that it's a charge of 2Q. So to do that, I'm going to add twice as many field lines, and I'm still trying to make them the same length, but as you can tell, I'm sort of eyeing it, so there's a chance that it's going to be a bit of an error in it, but either way, I think you understand the point. So that's the way the electric field lines for a charge of 2Q looks as opposed to a charge of Q. Additionally, if it was a negative charge, you would have exactly the same. If it was negative Q, for instance, you'd have exactly the same field lines that you see in our charge Q, except the field lines would be pointing towards the charge instead of away from the charge. Same thing with the 2Q, you'd have exactly the same 8 field lines, all the same length, but they would all be pointing towards the center of the charge as opposed to the pointing away. So that's the key thing to understand. Then you can start to make some sense because it turns out the Gauss's law can actually be stated like this. This is Gauss's apostrophe S law. And basically it says the electric flux from a closed surface the electric flux through any closed surface is directly proportional to the charge enclosed. So that really is Gauss's law. The net electric flux from any closed surface is proportional to the charge that's enclosed in that surface. And it turns out the constant of proportionality is just the epsilon that I told you was so important, because it turns out it's Q enclosed over epsilon naught. So that really is Gauss's law. Now you can start to see, oh, okay, so the by thinking about the flux as the number of field lines that penetrate a surface, you could see that the charge 2Q would, if you surrounded it, say, by a sphere or something, it would have twice as many field lines penetrating the surface of that sphere than if you put the sphere around the charge of 1Q. Okay? Does that make sense? Anybody have any questions on that? All right. Now that we have that, I'm going to write Gauss's law in the more robust form. I'm sort of inclined to just derive it and then write it. Yeah, I think I'm going to do that. Okay, so what I'm going to do is I'm going to actually calculate the net flux caused through a arbitrary closed surface. Now, I say it's arbitrary, meaning any closed surface would give you the exact same result in some ways. But if I choose one surface as opposed to a bunch of others, then I'm my calculation will be a lot easier. So what I'm going to do is I'm going to imagine an XYZ coordinate system, and I'm going to put a charge positive Q at the origin. So let me do that. I'm going to take my black marker, and I'm going to try to draw a coordinate system. And the coordinate system, that looks pretty good. Now I'm going to take my point charge and I'm going to put it right at the origin. I'm hoping it's going to draw a nice circle for me. Let's see what it does. There you go. It drew a circle. And that charge is going to be Q. Okay, I don't want to write it on there because it'll obscure the figure that I'm getting ready to draw. Now, what we know is the electric field due to a point charge, the magnitude of that electric field is given by E is equal to Q over 4 pi epsilon naught r squared, where r is the distance you are away from the center of this point charge, which there's no center because it's a point charge, but from the origin basically. So the beauty of this is realizing that the electric field, when it's created by a spherical charge or by a point charge, it has a spherical symmetry. Meaning, if I set r to a constant, then that will define a shape that is spherical. And on that spherical surface, the electric field's magnitude will be a constant. So, knowing that, I'm now going to try to calculate the electric field over a closed surface, and I'm going to pick the closed surface very wisely. So the electric flux through this closed surface is going to be a closed integral. See how I've got the integral with a circle over it? That's something we use in physics, and it means, hey, this formula has an integral, but you're technically not supposed to apply this formula unless you're integrating it over a closed surface. And again, a closed surface is a surface that has a clear inside and an outside. For instance, if you take the little toilet paper roll or paper towel roll that you throw away when you run out of toilet paper or paper towels, you might think that's a closed surface, but it is true if you're inside of the tube, you could have to go through the outer cardboard to get to the outer surface, but because you could also go down to the end and then come out and then be out there. That's why it's not a closed surface. Now, if you took that paper towel or toilet paper roll and put a little cardboard lid on each end, then it would be a closed surface because it looks just like a soup can at that point. Similarly, a sphere is a closed surface because it has an inside of the sphere and an outside of the sphere, and the only way you can get from the inside to the outside is by going through the surface. That's the key thing. So this flux is going to be an integral over a closed surface of E dot dA. Now, dA is supposed to be a differential area element, meaning we're going to cut it up so small that the electric field should be fairly uniform over the whole surface area dA, and the vector dA will be perpendicular to that surface area and will point away from the interior of that closed surface. Okay. So, by the symmetry of the electric field, meaning it has a spherical symmetry, I'm going to choose my Gaussian closed surface to be a sphere centered on the origin. So I'm going to attempt to draw a closed sphere on the origin, centered on the origin, and that's going to be what we call our Gaussian surface. So let me see if I can draw it fairly neatly. Something like that. That looks pretty good. You can also see that that is, in fact, a three-dimensional sphere as we have it drawn like that. You could also see that the surface looks somewhat like this as well. I'm going to stretch this just a tad. That looks good. Actually, I better make that a little smaller. It wasn't as good as I thought it would be. Okay, that's good. Okay, so now you can see that really is a three-dimensional sphere. Now, if you look at that sphere, then you might want to take a little differential area element, which if you've had any experience with spherical coordinates, you'll recognize exactly what type of area I'm drawing here. It looks like a little bent window. That is exactly one of the differential area elements defined in spherical coordinates. Again, we don't have to know spherical coordinates for this class, but I did put intros to spherical coordinates in week 0 module. So I do recommend you look them over. I'm not going to make you calculate things with it, but it's helpful to have those specific vectors to refer to when I'm talking about Gaussian surfaces, and later when we start to do magnetic surfaces, magnetic fields as well. There's another law like Gauss's law that we'll use for magnetic fields, and we'll have to do some of the similar stuff. So there's my little dA vector, and that dA vector is not even very good because I it's supposed to be pointing radially outward, and you can see that's not really radially outward. Radially outward means that it should look as if it came straight from the origin. So if I go to try to do that and make it look like it came straight from the origin, then it'd have to be more like that. And I'm going to say dA has some magnitude dA, and it points in the r hat direction. So remember, we did cover some vectors, I hat, j hat, k hat. We also called those x hat, y hat, and j hat. They were all vectors that had hats on them. Does anybody recall what the vectors with hats on them mean? What the hat actually means? I have the chat window open in case you wanted to type it, but do either of y'all know that? It's okay if you don't. It's not very cool of me to ask when there's only two students. So I will tell you that the hat means it's a unit vector. That means the length of the vector is 1 unit long, not 1 meter, not 1 Newton, not 1 meter per second. It's just 1 unit. So if you actually calculated the magnitude of it, it would come out as 1.000 to an infinite number of zeros, and it wouldn't have any units. So the r hat vector is defined in spherical coordinates as basically if you draw your x, y, z axes and you choose any point in space, then you connect that point in space to the origin, then the r vector will be parallel to that line that connects the origin to the point, and it'll point outward, okay, away from the origin. And it will be exactly 1 unit long. So that's what the r hat vector is. There's also a coordinate vector in spherical coordinates called theta hat. And there's also another one called phi hat or phi hat. I always call it phi, but I think technically it's supposed to be pronounced phi. So I apologize. I'm going to repeatedly say phi and phi and mean the same thing. But those two are important too, and they'll come in handy later. But right now, we really just need the r hat vector. So now that I have that, I could, those of you who've had Calc 3, for instance, would know about these spherical coordinates and possibly would even know the differential area elements. You don't need it though, because the nature of the Gauss's law is the left-hand side, which is a closed integral of E dot dA. You're never going to integrate that. You're always integrating it. You're always going to get an answer that is the answer of an integral problem, but you're designing it in such a way that you never have to do quote unquote calculus. You're just going to reduce the left-hand side to some electric field magnitude times some surface area magnitude. It might be multiple terms, so you'd have E1 times A1 plus E2 times A2 plus 0. But that's what it's going to be. It's going to be 0 for some parts and E times A for other parts, and that's it. Okay, that's the big thing that makes you avoid the work. The main thing is though, you can't do that. You can't integrate the left hand side until you understand the symmetries related to electric fields based on your knowledge of Coulomb's law. Okay, so it turns out it's Gauss's law. It's not Gauss's helpful hint that sometimes works. It's a law. It actually always holds. The problem is, though, you can't use it the way we're going to use it, except in very specific symmetries. And those symmetries are spherical symmetries, infinite cylindrical symmetries, so like a infinitely tall soup can or infinitely tall Pepsi can, something like that, that would be acceptable, and infinite planes, flat, infinite surfaces. Okay, those are the three symmetries that allow this quote unquote weird trick of Gauss's law. Gauss's law is going to be a two-part equation, a left-hand side and a right-hand side. And the way we're going to work it is we're going to work out the left-hand side using a hypothesis, and then we're going to do the real work, the work that actually sometimes takes integrals and stuff. That's going to be done on the right-hand side, and that one when we're done with those two sides, we'll set them equal to each other and we're going to solve for the magnitude of the electric field. In other words, we're literally solving for the integrand in the integral. That's why it's so weird, and that's why only under certain symmetries can you do this trick. But that's what we're going to do. I'm going to show you what the right-hand side is by working the left-hand side for this problem. So notice if we assume the sphere has a radius big R, and like I said, the total charge inside is Q. If we do that, then we know because the charge is a point charge, and also if it happened to be a spherical charge, it would still be the same answer. But because the charge is a point charge, we know it has spherical symmetry. So I have chosen a sphere as the Gaussian surface, and you're going to have to choose a Gaussian surface every time, but you're going to choose it wisely so that every part of the Gaussian surface has the electric field both perpendicular to that surface and constant on that surface, or it's going to be parallel to that surface so that it comes out to be zero. That's your only ways you can do this. You have to choose a surface that is either everywhere perpendicular to the electric field and therefore makes the electric field constant on that surface, or it's going to be parallel to the electric field. The dA vector is going to be parallel to the electric field so that E dot dA is going to be zero. It's never going to come out to be all zero like that on the left-hand side, but there will be times where part of it's going to be zero, and you'll see that in the three typical symmetries. So what we can do now is we say hypothesis E, the vector E for the electric field, is going to be some electric field that depends only on the radial or the spherical coordinate r. Okay, so it only depends on the distance you are from the origin of the coordinates, which is obviously the location of the point charge. So we're doing that, and we also recognize that it's going to point radially outward. Now, if we found out later that q was negative, that's okay because the negative q is going to make the r become negative r, and the vectors will point the right way. So you don't have to worry about that. You just have to point out that it's pointing in the radial direction. So on the Gaussian surface, whoa, wait a second here. On the Gaussian surface, uh, R is equal to R so that E of R, which is the magnitude of the electric field, is equal to a constant. Okay? That's just from the fact that E depends only on R. Since it only depends on R, and R is the radius vector, if you will, or the radius coordinate. Because of that, R being a constant makes a sphere, and since the R is a constant and E only depends on R, it has to be a constant. So now I can calculate what the flux is. So what the flux? What is the flux? It's the closed integral of E dot dA. Now, again, we don't need to know the details of what dA is, so I'm sort of, uh, hiding that to some extent, but I can show it to you if you ever want. It's just not very useful to you because we're not going to have to integrate the left-hand side. So what's going to happen is I'm going to put the electric field, which is E of R hat there, and then I've got a dot product, and now I've got to put the dA vector there. Well, the dA vector is dA times r hat. Now, important thing to remember about both dot products and cross products. Cross products will become relevant later, but both of those are what we call linear operations. So that means, in the context of a vector linear operation, that means that you can take all the scalars that are multiplied by the actual vectors and you can pull them way out in front of the dot product and just let the dot product act on the vectors themselves. So in doing that, what I'm going to do is I'm going to say this is equal to the integral of E of R times dA. And now I'm going to write the dot product as R hat dot R hat. Now remember, in general, a dot product, A dot B, is supposed to be the magnitude of A times the magnitude of B times the cosine of the angle between them when they're tail to tail. Okay, so can anybody tell me what the magnitude of the R hat vector is? Exactly. Good job, Nathaniel. That's the nature of the little hat on top of it. The hat means it's a unit vector. So yes, in this case, R hat dot R hat is going to be 1 times the cosine. Anybody guess what angle is between R hat and R hat? Exactly. Good job, Nathaniel. And I bet probably Anahi got that too. So this little dot, right, R hat dot R hat turns out to be 1 times cosine 0 degrees, which is just 1. And remember, I told you E of R was technically a constant. And in fact, when I put it there, I should say well, let's write it this way on Gaussian surface, R is equal to big R. So by saying that, what I mean is this little r is technically not little r, it has to be big R. And that's what makes this what we call a surface integral. It's a surface integral because we've evaluated the integrand on the surface of the sphere that we're integrating over, in this case, the Gaussian surface. So the fact that this is E evaluated at R means that E of R is in fact a constant, as we already told you. So I can pull that straight out in front of the integral, and we are going to get, oops, I had to go back to blue. We are going to get E of R times the integral of dA. Now, you know from the fundamental theorem of calculus that the integral of dx is just x, and therefore the integral of dA is just a. Well, A means the surface area. So we're adding up all those individual itty bitty areas until they add up to the surface area of a sphere. And the surface area of a sphere is a formula you should know, and you're now going to have to commit it to memory. And I don't know why I wrote all this in purple. It's supposed to be in blue. So we're now going to evaluate this integral without actually doing an integral. Oops, that's going to be E of R times the integral of dA, which equals E of R times the area A, but the area A, like I said, is the surface of a sphere. So that's going to be 4 pi R squared. So that's the surface area formula you should know. The surface area of a sphere is 4 pi R squared. The volume, which you don't need to know for this part, is 4/3 pi R cubed. That comes in handy later when we're doing the other side. So what we have now is we have managed to figure out exactly what the left-hand side of this integral will be. Now, the right-hand side of Gauss's law is technically this. So the Gauss's law is actually the closed integral of E dot dA is equal to Q enclosed over epsilon naught. So what I just worked out was the left-hand side. So normally the way I start off such a problem is I say left-hand side, and then I start calculating it. So I'll say this is the left-hand side. Now the right-hand side of the integral of the Gauss's law is Q enclosed over epsilon naught. Can anybody tell me what charge is actually enclosed inside that green Gaussian surface? It's just the charge Q, which y'all probably would have figured out, but it's a sort of open-ended question. It might seem kind of confusing. So that's literally the right-hand side. Okay. Now you're going to see exactly what Gauss's law allows us to do in this weird way that's only valid to do this under certain symmetry: spherical symmetry, infinitely long cylindrical symmetry, and infinitely large flat planar symmetry. So now I'm going to say left hand side equals right hand side. And from that, that gives me E of R times 4 pi r squared is equal to, in this case, we got Q over epsilon naught. Now, that Gaussian surface could be any radius r. I just chose a capital R so we wouldn't confuse it with a coordinate, but it's not locked at some constant. It can be any value r you want. So now we can see from solving this left-hand side equals right-hand side, we can see that E of r is actually equal to Q over 4 pi epsilon naught r squared. And that's exactly the formula that Coulomb's law gives us. And in fact, if we compare it with our hypothesis, we've got E, the electric field, is equal to Q over 4 pi epsilon naught r squared r hat for any arbitrary r. And that's it. That's, oops, my stupid program. I hate how it always switches to a eraser. All right, so that's actually how you implement Gauss's law. I was going to do the derivation thing where I'd work it out and integrate all that, but I figured it might be best to just jump right in and show you how we're actually solving a Gauss's law problem. So that Gauss's law problem would be something along the lines of uh, use Gauss's law to calculate the electric field at some distance r away from a point charge q. Okay, so that's what I did. Notice the steps. Gauss's law is the closed integral of E dot dA equals Q enclosed over epsilon naught. The first step is you look at the charge distribution and make a hypothesis about what the electric field is like. In other words, a functional value that includes what the magnitude depends on as well as what the directions are. My hypothesis was E, the electric field, is equal to E, some function of R due to spherical symmetry, and that it points radially outward. So I wrote times R hat. Okay, that was my hypothesis. Once you have the hypothesis, then you write down the left hand side of Gauss's law and you go through the act of integrating. You're technically not, you technically are integrating, but you're integrating using a Gaussian surface that you contrived specifically based on the shape of the charge distribution so that it would be a constant everywhere on it are zero. So the electric field and the Gaussian surface are sort of working together to make the left-hand side a trivial integral that will turn out to be just E times A or E times A plus 0 or E1 times A1 plus 0 plus E2 times A2 or something like that. It's always going to be some electric field magnitude times an area magnitude. Okay? So now that we have that, oh, and then that was the left-hand side. Then you use the right-hand side, which is Q enclosed over epsilon naught, to calculate the total charge enclosed, and you divide that by epsilon naught, and then you set the left-hand side equal to the right-hand side, and you solve for that hypothetical magnitude of the electric field that you got, and that is the actual goal. You're trying to get the magnitude of the electric field for some sort of arbitrary charge distribution. So that's how you do it. Anybody have any questions on that? Now, your book talks a lot about uh, how the Gaussian surfaces, you can put them around one charge or two charge, but if they actually are around no charges, every field line that enters it will also exit it. So the net flux is zero. That's why it's always Q enclosed over epsilon naught. Not only that, if you put a positive and a negative charge of equal magnitude inside of one Gaussian surface, then the positive Q added to the negative Q means the total charge enclosed is zero. So the net flux in that case is going to be zero as well. There's a whole lot of things you can do with that, and you'll see them as you're reading your book. But the main thing is you have to read your book to get it. Anybody have any questions on this before I move to the next example? Okay. So your book has a lot of nice conceptual examples, like conceptual example 22.2. Those are all helpful. You need to do it, but it's more important that I teach you how to do the actual computations. I definitely want to talk to you about the conceptual stuff, and I'm going to expose you to that as we're solving problems. But I really rely on you working on your concept questions, reading your book, and asking me for any questions you might have. So I'm going to start with example 22.3. It says a charged spherical conducting shell, a thin spherical shell of radius r0 possesses a total net charge q that is uniformly distributed on it. Figure 22-11. Determine the electric field at points A outside the shell, B inside the shell, and C, what if the conductor were a solid sphere? Okay, so this is going to be example 22. I call it 22.3. Again, I'm going to draw a coordinate system. I hate it when this happens. It's going too slow. There it is. Okay. So there's my XYZ coordinate system. Just I didn't point it out last time, but this is the y-axis, that's the x-axis, and this is the z-axis. Now, what I have is a spherical charge distribution. So I'm going to draw my spherical charge distribution in blue. And this one I'm going to make a little bit bigger. I'm going to imagine it, for instance, being right here, here. So I'm going to draw like that. So there's my spherical shell. Now, the spherical shell has a total charge Q that's uniformly distributed on the outside of it. Gauss's law can be used to show you that if you tried to put that charge inside the sphere, inside the spherical shell, it would automatically repel itself to get out on the outside surface. So the total charge is Q. I'm not showing it on here because obviously it would run into problems obscuring my diagram. But what I am going to do is I'm first going to imagine a Gaussian surface of r less than the radius of the sphere. So the radius of the sphere, I'm going to say, is from here, oops, from here to here. I'm going to call that distance r0. Now I'm going to make a Gaussian surface inside because actually I'll make it outside first because part A wants to know the electric field outside. So I will draw the electric field outside. Oops, I need to draw that with an automatic circle on. So I'm going to try to draw it a little better. Okay, so there's a Gaussian surface that is a sphere centered on the center of the sphere that exists there. The radius of this one I'm just going to call r. So what I'll do in this case is I'll say this distance right here. Oops, that's not that great because it's still trying to draw it automatically. So I'm going to say this distance from here to here is just plain r. And what I'm going to do is say hypothesis E is going to equal E of R hat. Again, I think because of the spherical symmetry of the charge distribution, I expect the electric field is going to be spherically symmetric as well, and therefore I can go on the assumption that my Gaussian surface should be a sphere. That's why I drew the sphere, and therefore, because of the electric field magnitude only depending on a constant r, the E of r is going to be a constant. So I have that. I have my Gaussian surface. Notice I had to recognize the symmetry of the electric field before I could actually choose the electric field hypothesis and before I could choose the Gaussian surface. The good news is there's only three choices, so you're going to repeatedly use a sphere for a sphere. You're going to use a soup can for an infinite cylinder, and you're going to use a soup can a different way for an infinite plane. So that's all. That's all three scenarios that you have to learn. Now that we have that, we can write left-hand side, the closed integral of E dot dA. It has to be on the surface of the Gaussian surface, so that's going to make it E of R. Notice I'm using the actual green R that we had drawn, just like last time I used the big R, but this time I'm using the little r. R hat dot dA R hat. And again, the differential area vector for a spherical surface is just some dA times R hat. Again, I could tell you exactly what that would be in spherical coordinates, but we don't need to do it because we're not going to have to do this integral on the left-hand side. Now, because we're integrating on the surface of the sphere, the E of R is a constant, so I'm going to pull that out in front. And now I'm going to have dA, the integral of dA times r hat dot r hat, but r hat dot r hat is 1. So I end up getting E of r times the surface area of the Gaussian sphere, which is 4 pi r squared. So that's our left-hand side. The right-hand side, however, the right-hand side is Q enclosed over epsilon naught. The Q enclosed is just the plain Q charge, which I never wrote up there, but I did tell you what it was. Let me go ahead and write that down. So that's the charge there. So the Q enclosed is just plain Q, and we have Q over epsilon naught. It'll get more complicated, and this is the part that gets more complicated. I'll show you that one with a solid sphere in a second. So now I say left-hand side is equal to right-hand side. And with that, I get E of R times 4 pi R squared is equal to Q over epsilon naught, which says E of R is equal to Q over 4 pi epsilon naught R squared. Now, going back to our hypothesis, that tells us E, the electric field, is equal to Q over 4 pi epsilon naught R squared R hat, and this is for R greater than R0. Okay, that's because that's the only region that I actually worked out Gauss's law for. Now I'm going to draw another Gaussian surface inside of the sphere to cover for cases of R less than R0. So I'll draw another Gaussian surface, and it's again going to be a sphere, and that one turned out terribly because I didn't have it on auto draw. There you go. So there's my Gaussian surface for R less than R0. So in this case, we're going to say again, part B. This was all part A, by the way. So part B is for R less than big R, or less than R0. So our hypothesis is again, E is equal to E of R hat. And the Gaussian surface, again, because of the spherical symmetry, we expected it to be a Gaussian surface that was spherical, centered on the center of the sphere. So we can now say left-hand side and the left-hand side is going to be the closed integral of E dot dA, which we know is going to work out to E of R. And again, this case, the R is less than R0 times the integral of dA times R hat dot R hat, which is 1. So we're going to get E of R times 4 pi R squared. So that's our left-hand side. Our right-hand side, on the other hand, is Q enclosed over epsilon naught. Again, your book will make these discussions, but I'm telling you that if you apply Gauss's law to a metallic shell, you can create the Gaussian surface just inside of the metallic shell, not outside of the shell, and because of the fact that electric field inside of in electrostatics, an electric field in a conductor is zero. It has to be zero. And because of that, Gauss's law, the closed integral E dot dA for that Gaussian surface would be zero. And because that's zero, that means the charge enclosed must be zero. Therefore, you reach the conclusion that all the charge is oriented on the outside edge of the shell. So in this case, the charge enclosed is just zero, and that's just zero. So for R less than zero, or R less than R0, we get E is equal to zero for R less than R0. And it turns out that in general, when you have when you're calculating the electric field perpendicular to a surface from one material to the next, there's only a discontinuity there if there's a surface charge. And in this case, there is a surface charge. So if you actually make a plot of electric field versus distance r, for this case, what you'd see is going to happen is we would have I'm going to use red to graph this, out to a radius r, 0, out to a radius r0, the electric field is in fact 0. Then all of a sudden, it's going to jump up to another quantity, and then it's going to fall off like 1 over r squared. Okay. Now, what we see here is a discontinuity, and that discontinuity is actually equal to, if we look at what the actual function should be, right here, this is going to be Q over 4 pi epsilon naught r squared. Actually, I shouldn't even try to draw that. I'm going to draw it over on the other side so it won't get so crowded. This electric field E is Q over 4 pi epsilon naught R0 squared. That's the value at that particular spot. So the discontinuity you can see is actually Q over 4 pi R0 squared divided by epsilon 0. Notice the Q over 4 pi R squared has units of coulombs per square meter. That's because the discontinuity is supposed to be sigma that we talked about before over epsilon naught. So discontinuity of E perpendicular, not parallel, is sigma over epsilon naught. So that's what we just found. Sigma, remember, sigma is dq over dA, which in this case happened to be q over 4 pi r0 squared. Okay, any questions about that? Now, if the last part, it says, what if the conductor were a solid sphere? If the conductor were a solid sphere, we'd still get the same result. The reason being is because now, instead of it just being a conducting shell, the whole insides is nothing but conductor. Again, the rule for electrostatics, which is meaning when you don't have batteries connected to drive current, the electric field inside of any conductor is always zero. Therefore, if we applied Gauss's law to a spherical conductor and we used a Gaussian surface that was just barely inside of the conducting spherical chunk, then the electric field, the left-hand side, closed integral E dot dA, has to be equal to zero because the electric field's zero. Well, the left-hand side has to be equal to the right-hand side, and the right-hand side is Q enclosed over epsilon naught. The only way we can get that to be zero is if Q enclosed is zero. So that tells us that when you have a solid conducting sphere, and actually it's really true for any solid conducting shape, all of the charge of the that might be put on that conducting chunk will be distributed all on the outside surfaces, not any side anywhere inside. Any questions on that? So remember, everybody, I did part C verbally, so you need to make sure you can do that. What I'd like to do now is actually, yeah, it's, example 22.4. So this one is a solid sphere of charge. This one's not a conductor, though. This is a non-conductor, and we're going to go on the assumption that the solid sphere has a uniformly distributed charge rho throughout its volume. It says an electric charge Q is distributed uniformly throughout a non-conducting sphere of radius r0. Determine the electric field A outside for r greater than r0 and B inside for r less than r0. So that's our problem. I'm going to again draw a coordinate system, something like that. That looks pretty good. Again, X, Y, Z doesn't matter too much. The main thing is, in this case, we're going to have a non-conducting sphere of radius r0. So there's my charged sphere, and that means it has a total charge Q, and that charge is distributed everywhere throughout it. So you can see there's a little plus here, a plus there, so on and so forth. I'm not going to draw that. Our Gaussian surface for r greater than zero is going to be a sphere again because the spherically symmetric charge distribution suggests, like we learned from Newton's law of gravity, that this 1 over r squared law it forces any spherical charge distribution to be spherically symmetric so that the electric field will literally only depend on R. With that in mind, I'm going to draw a concentric spherical Gaussian surface. So here's my concentric spherical Gaussian surface. That wasn't as great as I'd like it to be, but it didn't turn out too terribly bad. Okay, and I'm trying to make it centered up as best we can so we can, have it accurately reflect the problem. That's pretty good. That's good enough anyways. So what I'm saying here is this radius is R and this radius is R0. Okay. Charge is distributed throughout. That means basically rho equals a constant, and that constant is dq over dv. Remember, that's charge per unit volume. That's going to come in handy. Okay. So my hypothesis is E is equal to E, a function of R, times r hat. Again, spherical symmetry, that's all you're going to do every darn time. Okay, you're going to see when I do the cylindrical one and when I do the flat surface one, you're going to see there's a special case there, but it's always the same thing. So it's not that hard. Now I'm going to say left hand side. The left hand side of Gauss's law is the closed integral at E dot dA. Again, using the exact same setup we did before, this is going to turn out to be E of r, the radius of the Gaussian surface, times the integral of dA times r hat dot r hat, which again is just 1. So we get E of r times 4 pi r squared. Notice it's exactly the same answer that I got the last two tries, actually all the last three, the two parts of the previous problem and the first one we did. Now I'm going to do the right-hand side, and this is where you could, in principle, use calculus. However, we try to avoid that if we can do it easily. If it's hard, then yeah, it's just be easier to. If it's easier to do the calculus than it is to do the tricky ways, then it's better to just do the calculus. But in this case, I'm going to show you the easy way, and I'll at least give you a hint as to the hard calculus way. The right-hand side is Q enclosed over epsilon naught. Now, generally speaking, if we wanted to do the calculus, Q enclosed is got to be for a distribution of charge that's uniform throughout the volume. That's going to have to be the integral of rho dV. So we could, for instance, take the differential volume element to be 2 pi, or excuse me, 4 pi r squared dr. In other words, it's 4 pi r squared, the area, surface area of the inside edge of the spherical shell, and then dr is the thickness. So we get basically a spherical shell, and then we'll integrate that from r equals 0 to r equal r0. And by doing so, that would actually give us the total charge within the sphere. Okay. Now, in this case, all the charge is completely enclosed, so we don't have to really do anything like this because we know the total charge in this case is Q, which is also equal to rho times 4/3 pi r0 cubed. Just so you'll know that you could see what rho would be. Rho would be Q over 4/3 pi r0 cubed. That's why I took the time to write all that. It wasn't necessary, but I did do that. Now, that means the numerator of the right hand side is just Q and the denominator is epsilon 0. So now I take left hand side, set it equal to right hand side. And when I do that, I get E of r times 4 pi r squared is equal to Q over epsilon naught. And this, of course, is the same thing we found every time so far. And that is E is equal to Q over 4 pi epsilon naught r squared times r hat for r greater than r0. In this case, we're not going to have a surface charge, so I know already that this is going to be for r greater than or equal to. You don't see that yet, but you will in a few. So there's part A. Now for part B, we're doing the same thing, only this time I'm going to integrate over the Gaussian surface that has a radius smaller than r0. So I'll draw the Gaussian surface here. And the Gaussian surface in this case would be that sphere right there. And I don't know why I obsess about getting it perfect, but that's pretty close. All right, so there's my Gaussian surface for the other part. Now, for part B, oops, for part B, my hypothesis is still going to be the same thing. E is equal to E of r hat, and then the left-hand side of Gauss's law, the closed integral E dot dA, is going to equal E of R times the integral dA times R hat dot R hat, which is 1, and therefore we get E of R times 4 pi R squared. Notice is exactly the same answer that we got the last 4 times. Okay. Now I got to do the right hand side, and this is where the hard part, the potentially hard part comes in. So the right hand side is Q enclosed over epsilon naught. And what we'd have to do is we could take the integral of rho dv and integrate from 0 to r. In other words, only out to the Gaussian surface r, not all the way to r0. And we'd integrate that, and the rho, of course, would be that constant that's 3 rho over 4 pi r0 squared. That's a way that we could do it. But we're actually smarter than that, and we can avoid calculus by doing it this way. So what we're going to do is we're going to say rho. Oops, I don't know why it does that. Okay, so something weird just happened there. So what I'm going to do is I'm going to say rho equals a constant. Well, that constant for the whole sphere is Q. Notice it's Q times 3 because it's 4/3 in the denominator, and when you divide by a fraction, you flip the fraction over. So it's 3Q over 4 pi R squared. Well, that also has to equal the Q enclosed over the volume of the sphere, the Gaussian sphere. So that means in this case, oh, that was R0. I got to make sure I put the R0 there because that's for the total chunk of spherical charge thing. The radius is R0. For the Gaussian surface inside, the radius is just R. So it's 4 pi R squared here. You can see immediately that the 4 pi and the 4 pi cancel out. Oops. We also need a 3 up top. The 3 and the 3 on the other side cancel out as well. So from this, we're able to reach the conclusion that Q enclosed is actually equal to the total charge times R0 over R squared. Okay? So with that in mind, we can go ahead and write this as Q over epsilon 0 times, oh, I put the R0 on the wrong spot. Watch that, everybody. When I solved for Q enclosed, I switched them in a second, and it's actually R squared over R0 squared. That's what it's supposed to be. So now, instead of Q over epsilon naught, it's going to be Q times R squared over epsilon naught times R0 squared. Now I can say left-hand side equals right-hand side. And that gives me E of R times 4 pi R squared is equal to, oops, left off the epsilon 0 over here. Oh, no, I didn't. That was the right place. I was looking at the wrong line. This is what I was thinking I was looking at, and I thought I'd forgot the epsilon 0. So now I've got Q over epsilon 0 on the right-hand side, but I also have times R squared over R0 squared. And actually, that's supposed to be cubed. Everybody check that because we were supposed to do volume, and somehow when I wrote this, I ended up writing it like a dummy and wrote it R squared instead of R cubed. So I'll write this in a different color so you guys will notice that I fixed it. So this is going to be 3 and this is going to be 3, and that means this is going to be 3 and this is going to be 3. I'll write those in the color that we had originally planned. So that's R cubed over R0 cubed. And I already had this one correct. The main, and this is what made me see it, the main thing was I realized it was going to be linear. The electric field's supposed to be linear inside. and we couldn't get that if the r squareds cancel out. So what we see is the r squared cancels out with the 3 over here and just leaves a 1. And now we can say that our electric field, E of R magnitude, is equal to Q times R, meaning it's linear, over 4 pi epsilon naught R0 cubed. And that all looks good. Therefore, our electric field is equal to Q over 4 pi epsilon naught R0 cubed times R hat, and that is for R less than or equal to R0. And you can now see why I said it would be less than or equal to, because if I plug in R equals R0 in the formula for A, R in the formula for B, I get the same answer. So that shows the electric field is actually continuous. And in this case, it's specifically the perpendicular component of the electric field is continuous from one substance to the next. So you could have done all that stuff with integrals, and that's all great. I mean, if you want to do it that way, that's fine. But if integrals are even remotely difficult, it'd be better to just use straight up, ratios and proportions like I did here. Anybody have any questions on that one? All right, we only got 5 minutes left, so I want to tell you what we're going to do when we do infinite cylindrical charges. Like, for instance, the very first problem we solved when I gave you the electric field in vector form, remember it was dE equals dQ times RP minus RdQ, close parentheses, over 4 pi epsilon naught absolute value bars, meaning the magnitude of RP minus RdQ cubed. When I used that, the first thing I did was an infinitely long wire. Well, we could do that here, and if I did so, it would look like this. So here is my X and Y axis. That's really all that matters in this case. I'm going to say that's X. I'm going to say that is Y. And yeah, that all works. And I'm going to imagine finding out what the electric field strength is some distance away. So what I'm going to imagine right now is I have a cylindrical long wire. So this goes on to negative infinity and this goes on to positive infinity. And it has a charge per unit length lambda. Okay. And what I'd like to know is what is the electric field out at a distance r? Well, at a distance r, the easiest thing we can do is make a Gaussian surface whose radius is r. And I'm drawing it like a box right now, but that's because that's what its shape is. It's actually going to be a soup can like that. Okay, so that's our actual Gaussian surface. The straight line on the top and bottom didn't need to be there. I just sort of did that so you'd understand sort of what the shape was. So I can kill that now. But that's exactly the same shape that you're going to use when I tell you to do an infinite plane, except here the soup label surface of the soup can is what's important. And when you do the infinite plane, it's actually the lid and the bottom of the soup can that are important. So, in now looking at this Gaussian surface, we're going to have a couple different dAs. For instance, we're going to have this dA right here, and that dA is equal to dA r hat. Then we're also going to have a dA up here. That dA, I'm going to call this SL for soup label. This is dA top for DAT for top. This is going to be dA K hat. And then down here, we're going to have a dA bottom that's equal to negative dA k hat. Okay, so that's our Gaussian surface for this particular problem. Oops. And remember, this is an infinite wire that goes on for infinity up and down. So doing this, we can go ahead and make our hypothesis. And our hypothesis is E is equal to some E of R, and I'll put CYL on there because this isn't the spherical coordinate R. This is the cylindrical coordinate R that only points radially outward in the X and Y plane. You can move it up above the X and Y plane, but it's still only going to have X and Y components. So I just subscripted CL, and it's going to point in the R hat direction, but that R hat direction is the cylindrical coordinate R hat direction instead of the spherical coordinate R hat direction, which would have an actual K hat term. Okay, so now I can write the left hand side, closed integral E dot dA. You see the surface of the Gaussian surface that obviously has a radius R, say. In this case, I'm going to put in my E of R, which on the surface of the cylinder is going to be a constant. So I've got to do an integral over the soup label plus an integral over the top plus an integral over the bottom. That's what you have to do to make a closed integral. It's got to take into account all the surfaces. So for the soup label, we're going to get E of R hat, and I'll just put a subscript C on there instead of the whole thing. And that's going to be dA R cylindrical hat plus, in this case, at the top and bottom, the E is going to vary. It's not going to be a constant out there. It's going to have various R's. So I'm going to write E of R hat dot dA K hat. And then I'm going to also write plus the integral E of R. That one was over the top. And this is E of R hat. Again, cylindrical, 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 cylindrical. But this time it's going to be dotted with negative dA K hat. Now, seems a little more complicated, but notice on the soup label, the E of R is a constant. So that's just going to, and by the way, it just reached 650. So you guys are free to go. I'm going to finish this example, but you're free to go. Let me finish this example. And if anybody's still here, I'll take questions. But like I said, you don't feel obligated to stay. This is E of R times the integral of dA times R hat cylindrical dot R hat cylindrical, which of course is still 1, plus when you do the dot product of this other one, it's going to be R hat dot K hat, which is 0 because R hat is only X and Y and K hat is only K in the Z direction. So they're 90 degrees to each other. So that's going to be 0 and plus the integral dot dot dot. This one was the top and this one was the bottom. And this one's going to be R hat dot K hat again, which is 0. So this is what I was talking about, how you'll get E times an area, maybe plus a 0 or something like that. So now all I have is E of R cylindrical times the surface area of the soup label. The surface area of the soup label is 2 pi R times this distance, which I'm going to call L. So it's 2 pi R times L. I should probably write that in purple. So that's the right-hand side. Now the left-hand side, or excuse me, that was right-hand side. So now the right-hand side, we've done the left-hand side. The right-hand side is Q enclosed over epsilon naught, and Q enclosed is just going to be lambda times L. That's the reason I taught you those dk or dq is equal to lambda dl or sigma dA or rho dV. So the Q enclosed is just lambda L over epsilon, and then all that will be over epsilon naught. So now I set left-hand side equal to right-hand side, and that gives me that gives me E of R cylindrical times 2 pi RL is equal to lambda L over epsilon naught. Notice the L's cancel out, and we're going to get exactly the same expression that we got when I did it that complicated way with Coulomb's law. We're getting lambda over 2 pi epsilon naught R, technically R cylindrical, times technically R cylindrical hat, and that's it. All right, so I've got you through quite a bit. You guys are obviously, like I said, you were free to go a long time ago. I've spent 4 extra minutes, so I went over by 4 minutes. Does anybody have any questions?
Hey, I have a question.
Yes.
I was wondering, with your test coming up, is there any sort of study guide or like a past test we could look at to know what's going to be on the test?
Yes, I've spoken quite a bit about that. There's a practice test that was made. It's actually exactly the same as the practice test we had for online test two. So if you've been doing that one, that was useful up until the online test was due. But now there's another one. It's called PT 03 or something like that, and then it says F2 FT01. That's the practice test, and it's actually the questions that are used on that question on that practice test, because each time you take it, it'll be a different set of questions. Those questions are the exact questions that'll be on the test. Now, there's a lot of them. It's not like it's just four or five, but if you did it an infinite number of times, I guarantee that 80% of the points will come from those questions. But this time I actually did 100% of the questions coming from those practice questions. So uh, let me answer this question right now. Oh, that was Miles. Okay, Nathaniel said, "Are we going to have a Zoom meeting? We can take the test on Sunday morning. I saw your email. The 9 a.m. option would be great for me, but I wasn't sure if it was happening or not. I'm still waiting on the rest of the people. I've got three people now that are in the midst of figuring out whether I can take it at 9 o'clock or 9:30 in the morning or 10 a.m. in the morning, or if I had to stick to three, which is what I originally promised. As soon as I get that, which has to be by 11:59 p.m., I'll know. So tomorrow morning, I'll know definitively whether we'll do it. I'm pretty sure what I'll probably do is I'll probably hold one at 9, and then if I can't get the other person to agree to come to the 9 one, I'll just have to do another one at 3. No, that's not a stupid question. That's cool, bud. Anybody else have any questions? There's no stupid questions with Mr. Younger. Okay, so the 9. Okay, that's cool. I don't mind doing the 9 at all. That just eliminates the 9:30 and the 10 o'clock option. My other student that couldn't make it anyone, I wasn't sure 10 o'clock would be late enough for him because he has to be at work at I think at noon. So that literally only give him 30 minutes after he finished the test, and that's if everything went well. So I will probably lean towards 9, and everybody that sees this video will see that. Any other questions? Well, thanks for coming, everybody. I do appreciate it. This will seem a little bit like mind blowing, this Gauss's law stuff I just did, but watch it over and over. Listen to my words of encouragement. The fact that you're really only going to have three shapes for your Gaussian surfaces, and you're just going to use them over and over again, so it shouldn't be that bad. Uh, can you post an announcement when you figure out the time for Sunday? Other than I'm good. Yeah, I will definitely do that tomorrow morning, and I'm probably 99.9% sure it's going to be 9 a.m. So don't worry too much about that. Anything else? Oh, that's it. Well, let's stop the share. Well, thank you for coming, everybody. Have a good one. Bye bye.